Hello and welcome to yet another video of Cornerstones of Math. Today we are going to solve a slightly challenging problem on counting the number of functions. In fact, about 2 months ago, I have covered a much easier problem than this one, so feel free to check that video if you haven't watched it. In this video, I have brought up significantly leveled up problem, so let us take a look at it. For a set X having n elements, x1, x2, x3, xn, and a function f from x to x, the first problem says find the number of functions f such that the range of f has n-1 elements. And the next problem says find the number of functions f such that the range of f dot f, the function composition, has n-1 elements. And since this problem is actually quite challenging, there's a hint. Before thinking about the range of f dot f, think about what must be the number of elements of the range of f. Alright, now let's start from the first problem. Finding the number of function f that the range of f has n-1 elements. Obviously, the first step should be choosing n-1 elements from n elements of x, so that these n-1 elements are the elements of the range of f. For example, in this choice, the last element xn is unselected so that the range of f has n-1 elements. But this is not the only way of choosing n-1 elements. There are total n choose n-1 choices for that. Pretty simple so far. And just for the sake of clarity and easier explanation, let us use following notations. Let's call the range of f as set y and refer to its elements as y1, y2, y3, so on, up to yn-1. Then we have one unselected element xk, which only matters in the next problem, really. Next, we must construct a relation that correlates all n elements of x with exactly n-1 elements of the range y. And here's an important observation. Since x has n elements and y has n-1 elements, in every possible relation, two elements from x must be matched with the same element of y. In other words, there exist two distinct elements of x, xi and xj, such that f of xi equals f of xj. Once such xi and xj are determined, then we can think of this process like this. If we consider xi and xj as a single variable that just corresponds to one element of y, the problem reduces to matching n-1 elements of x with n-1 elements of y in a way that the relation is one-to-one correspondence, also known as bijection. So we can calculate the number of cases like this. There are n choose 2 ways to choose such xi and xj, and for each choice, the number of one-to-one correspondences between sets having n-1 elements is simply n-1 factorial. Combining this with the result of previous step, the total number of function f such that the number of elements of the range y equals n-1 is n choose n-1 times n choose 2 times n-1 factorial. So n choose n-1 is n, and then n choose 2 is n-1 over 2. So this times n-1 factorial, which equals n squared times n-1 times n-1 factorial divided by 2. So that was the first problem. Now let's move on to even more interesting one. Finding the number of functions f such that the range of function composition f dot f has n-1 elements. In this problem too, we use y as the range of f, and let z be the range of f dot f, which is also a subset of x just like y. And the number of elements in z must be n-1. There's actually a hint to this problem, so as the hint suggests, before thinking about the range of f dot f, let us first think about the possible number of elements of the range of f which is y. In this video, I will denote the number of elements of y using absolute value notation, but the notation ny is also commonly used to indicate the number of elements of y. First, what if the number of elements of y is n? In this case, f is one-to-one correspondence, also called bijection. But this also makes f dot f an one-to-one correspondence. Hence, the number of elements of z also must be n. Therefore, the number of elements of z cannot be n minus 1. Next, let us consider every cases where the number of elements of y is less than or equal to n minus 2. Now, if you think about it, z is a subset of y because of the nature of function composition. Therefore, the number of elements of z is always less than or equal to the number of elements of y, which is less than equal to n minus 2, so the number of elements of z cannot be n minus 1. Therefore, the only possible case is that the number of elements of y must be n minus 1. Only then the number of elements of z can be n minus 1. With that established, obviously the next thing to do is to find the number of ways to choose n minus 1 elements from x, which will be elements of y, which we denote as y1, y2, so on, yn minus 1. We have already seen in the previous problem that there are n choose n minus 1 ways for that. Also, there must be one unselected element xk of x, which does not correspond to the elements of y. In more formal words, there exists xk that belongs to x, such that xk does not belong to y. Now, before we think about the correspondence between x and y, let us first think about the correspondence between y and z. When performing f dot f, since this xk cannot be the value of the function, the second step f is performed only on these n minus 1 elements of y. This means that z, the range of f dot f, is actually f of y1, f of y2, f of yn minus 1. Moreover, since we are talking about the same function f that excludes this xk from its value, that very same xk is also excluded from z. This means that set z is the same as set y. Therefore, the second part of the function composition is simply the one-to-one correspondence or bijection from y to z or from y to y. The number of such one-to-one correspondences is n minus 1 factorial. So we have obtained this and this. And finally, the first f, the first part of the function composition. Our domain x have n elements, and we can actually write them as the n minus 1 elements from y, y1, y2, yn minus 1, and the one leftover element xk that doesn't belong to y. This part is actually simpler than the previous problem, because now we have established that these n minus 1 elements, y1, y2, yn minus 1, have one-to-one correspondence or bijection property, so they have no other choice but to be related with the same y1, y2, yn minus 1 in this middle y by the same bijection as in the second f from y to z. Therefore, we only need to consider the value of the function of this leftover element xk, and since f of xk also must be one of the elements from y, there are n minus 1 possible values for f of xk. And this is the stark difference between this problem and the previous problem. In the previous problem, y1, y2, yn minus 1 from domain x do not have to correspond to exactly n minus 1 elements y1, y2, yn minus 1 from set y. Let us think about this for a moment. For example, suppose that xk corresponds to some of these y's, say ym. Then it is also totally possible that y1, y2, yn minus 1 corresponds to only n minus 2 elements of y, excluding this ym. But in the second problem, that is impossible because the bijection relation was already established when we consider the second part of the function composition. Hence, the first part also must be bijection. So that's the big difference. And in conclusion, the number of function f such that the number of elements of z equals n-1 is n choose n-1 times n-1 factorial times n-1, which will give n-1 times n factorial. And that's all for today's video. Thank you all for watching, and please don't forget to hit the like and subscribe buttons, and I will see you in another video.